Hi, I'm Bridget, and the project I worked on this summer was investigating packing configurations of viral DNA and capsids under the advisement of Dr. Sean Walker. So real quick, a couple of applications of this is, of course, that DNA packing in viral capsids, and then also the mechanical packing of filaments or slender rods into containers. So for some background information, a capsid is the container of a DNA strand. So it contains it, protects it, and transports that DNA strand. And then the two main energies that are considered in packing are bending and torsion. So you can see right here the equation for energy. This first term is that bending energy. The second term is the torsion energy, and this over here is the other external forces that you may take into consideration. So what were we trying to do this summer? So we were trying to model and understand the packing of viral DNA, as well as alter an array of parameters that affect this packaging. So some of the constraints that we had to take into consideration are the inextensible attribute of the DNA strand, so you can't pull it, and then the self-contact, self-interaction that occurs in the packing, as well as the capsid. So what that means is our strand, as it's being packed into there, cannot go past the capsid border. So what was achieved, we found 4 main spooling configurations. We found the correlations between particular mechanical properties and packing configurations, as well as the regular spooling and randomized configurations require less energy. Those regular spooling and randomized configurations are part of the 4 main spooling configurations. So the first one that you see up here is the regular spooling configuration. So all these spools came in, relaxed on each other, and just fell down to the bottom of this capsid. As you can tell, the CBCT, these are the bending constant and the torsion constant. They're proportional to each other, so 1 to 1. This happened at a relatively low motor velocity, so it allowed the simulation to relax as it's going in. So that strand has the time to relax out to the sides of that capsid and give this overall look. Right here we have the vertical horizontal configuration. So these vertical spools occurred first, and then as the strand was being packed into this capsid, a kink occurred in the strand and it made these horizontal spools. This, again, was at a relatively low motor velocity, and as far as bending constant to the torsion constant, it's 3 times higher. And then down in the bottom left here, the main attribute of this configuration is a high motor velocity. So we have it at 0.6 here. So what this does is it doesn't allow the strand to relax as it's being packed into the capsid, and it causes this cylindrical look. And again, we have a CBCT of 3 to 1. And then the last main configuration that we have is the randomized configuration. So this happens when we have a very low bending constant, or just a low ratio of that bending constant to the torsion constant. And again, it happens at a relatively low motor velocity, so that strand can still relax, but as you can see, there's not really any spooling going on. So what were some of the parameters that we changed? So some of the ones that we changed that are noted here: the bending constant, the torsion constant, and the angular velocity. So for the bending constant, uniform spools cannot be made at low values or ratios to the torsion constant, which is something that you can see, right here. Yes. Sorry, it's hard to read this, the T and the B's. So when we have that low bending constant but a high torsion constant, the spools are created at first, but it doesn't have the parameters needed to keep that uniformity going, which causes this malformation right there. Another example of this is the randomized configuration, which can be seen over here, and that's just at an overall low bending constant. And then for moderate to high values, we have spools of plenty. They just want to keep happening. So for the torsion constant, it's a very iffy parameter. It has a sweet spot for spools. So if the bending constant is too high, but the torsion constant is low, spools happen. So that's this configuration right here. We have spools in vertical at this angle, and then another one back here. But when the bending constant is low and the torsion constant is high, we have spooling fail, which again is this right here. And then for angular velocity at low angular velocities, spools take a little bit longer to form. So the other two parameters that we mainly focused on are time duration and capsid motor velocity. So time duration was mainly used to take a look at the energy. So we found that the regular spooling and randomized configurations have the smallest energies after being packed. So down here you can see the cylindrical simulation at about 150 seconds, it's about fully packed, and that energy just shoots right up because for that cylindrical one, we saw this cylindrical configuration. When these spools are being packed into it, or the strand is being packed into it, it has to push these out to the sides of the capsid, so that requires a little bit more energy. And then we have the vertical horizontal, which requires a little bit more, or a little bit less energy, and then it just keeps going down to regular and then randomized. And then for the capsid motor velocity, it's somewhat of what you would expect. So when it's lower, it lets the strand relax more, which creates more uniform spools. And then when it's higher, it cannot make those spools because it can make the spools, but it doesn't make them go all the way out to the capsid. So it creates that cylindrical look, and it can also create a randomized configuration look. So what's next for this project in general? So what's next is to create a global vector field that extends the tangent vectors of the DNA strand, continue to improve the numerical method for faster simulations, and to develop more control over the packing configurations. Question? Is everybody hungry?
Do the strands have like a width, or is it just like?
Yeah, they have a diameter. So this one right here is 0.2.
Is there any way to tell, or I don't know if maybe this is something you looked at, was like for the different spooling configurations, which one like takes up a higher percentage of the capsid after like however many seconds or however much is pumped in, to see like which is like the most efficient, like taking up space? Was that like something that you could look at?
So that's something that you can look at by looking at the self-contact graphs, which I did not have here. So that just shows the contact that's happening with the strand as it's being packed in. And it progresses over time, so you can watch both the simulation and the self-contact graph happen at the same exact time. And you can, so spooling is something that we've kind of suspected to take up a little less room. It allows that strand, so like if you have a randomized thing, it has to push past some barriers and more energy and stuff like that. So spooling doesn't take up as much room. So something that we looked at with the self-contact graphs is to see if we have linear lines. So linear lines across our graph just symbolize to us like spools occurring. So as they're more towards the bottom and left, spools are occurring, and that is taking up a little less space. But we do have the capsid motor velocity, so the same amount of strand is pumped in. So we can't really do something with that, but we can look at the energies that are involved, which also with that and the self-contact graphs, it gives us somewhat of an idea of the how much is really in there and what it looks like.
Is there a specific configuration that you think is more common for other?
We think that the regular spooling configuration is more common for the viral capsids, but that is still something that we're currently looking into. And it was also a little bit surprising that we found that the regular spooling and the randomized configuration had around about the same low energy, but the regular was a little bit higher. So something that we would like to do, I'm not sure if I'm going to be able to do it, just because it's the simulation I want to run is probably going to take 12 plus hours. And what that would do is just go a little bit past that point, because what we were at for these simulations right here, this is about 70 to 75% packed, and you really don't get packed until you're about 80 to 85%. And we suspect that maybe those energies might flip, so the randomized might be a little bit higher because, like I said before, when it has that randomized configuration, that strand being packed in, it doesn't have like a really nice space to like fall into. It's got to push itself around, so that might increase the energy a little bit. And whereas the regular spooling gives it a little bit of that room. So this one's favored for room-wise, and maybe for energy, we just have to look at it at longer simulations.
What's the difference between the left and the right, like different like views, or is it like as it changes over time?
Left and right. Yes, this is over time. So this was done at, I want to say 3,000 time steps, and then this one right here is done at 55,000 time steps.
Okay.
So.
And then one more question. So like you're focused on like, you know, packing it in like the most efficiently and all that. Have you like taken a look at like how it would be like to like unpack it, or is that like outside the scope of this?
That's outside the scope of this.
I'm kind of curious like if it would be like, you know, putting it in easy one way would be the same as like easy like taking it out, or would it be, would you have to like interfere it to like the bonds and or the bends and all of that of the.
Yeah, that would be really interesting to look at, but this is more so of like the packing rather than the ejection of the DNA strand. So I think that would, it could definitely be like a branch off from this project, but not quite this project.
Just curious.
I am too.
Would it come out as headphones? Take headphones out of the
Oh yeah.
pocket?
Yeah. It doesn't really work.
I don't think it can get out the hole when it's all tangled up.
Yeah.
Anything else?